The universe is 23 trillion light-years across, and it's not 13.8 billion years old. What if the universe is just a cosmic shockwave? They told you the universe is 13.8 billion years old. They told you it stretches 93 billion light-years across. But here's the unsettling truth. That's only the universe we see. A bubble of light and time, defined by the simple fact that photons have only had so long to travel since the Big Bang. Beyond that bubble lies something stranger. At minimum, the cosmos must be at least 23 trillion light-years across, a scale so vast our minds can hardly hold it. And as for the age, the familiar 13.8 billion years is not the universe's true age at all. It is merely the age of our thermal history, the age of the fireball whose afterglow still lingers as the cosmic microwave background. But the universe itself, the greater whole, may be unimaginably older, perhaps eternal. We're going to leave behind the safety of the textbook numbers and ask a deeper question. What is the age and size of the real universe? Not just the observable bubble, but the unobservable vastness beyond. To find the answer, we'll need to explore cosmic geometry, the aftershocks of inflation, and radical ideas about cycles of time. And when we're done, you'll see why the familiar figure of 13.8 billion years is not the whole story, only the story of us. The universe is older and larger than you think. Let's begin with the story you've probably heard 100 times, the standard model of cosmology. The universe began with the Big Bang about 13.8 billion years ago. From an unimaginably hot and dense state, space itself began to expand. In those first few minutes, atomic nuclei formed. Hundreds of thousands of years later, the first atoms came together, and the universe released its first light, the cosmic microwave background. We still see that glow today, faint and stretched into microwaves by billions of years of expansion. From there, gravity pulled matter together. First gas clouds, then stars, then galaxies. Over eons, the great web of structure we see in the universe assembled. This is the grand timeline written into every astronomy textbook. And when you ask, how old is the universe? Scientists point to that timeline, 13.8 billion years. It's not a guess. It's derived from multiple lines of evidence. The expansion rate of galaxies, the ages of the oldest stars, the radioactive clocks in ancient elements, and the frozen patterns in the CMB. All of them converge on the same figure, with astonishing precision, 13.787 plus or minus 20 million years. And when you ask, how big is the universe? The textbooks say something equally startling. The radius of the observable universe is about 46.5 billion light-years. That means we can, in principle, detect light from objects that are now 46.5 billion light-years away in any direction. Double that for a diameter, and you get roughly 93 billion light-years across. Think about that. A fireball, 13.8 billion years old, spanning 93 billion light-years. On the surface, that seems paradoxical. How can something be younger than the distances we measure across it in light-years? Shouldn't the maximum size be 13.8 billion light-years across? 1 light-year for every year since the Big Bang? But this is where the standard story, while correct, starts to mislead us. It's the observable universe that's 93 billion light-years across. The actual universe, the unobservable part, could be far larger. And that 13.8 billion year age? It's not the true age of everything. It's just the age of the phase of the universe that led directly to us. Our thermal history. So the numbers in the textbooks aren't wrong, they're just incomplete. They describe our cosmic bubble, not the entire cosmos. And to understand the difference, we need to look deeper at why the universe appears the way it does, and why our familiar horizon is not the edge of reality, but a keyhole view into something much larger. Cracks in the picture. On the surface, the textbook numbers sound absolute. 13.8 billion years, 93 billion light years across. But the closer you look, the more those numbers start to crack. First, the geometry of space. When we measure the cosmic microwave background with exquisite precision, we find something astonishing. The universe is flat, not curved like a balloon, not saddle-shaped, but Euclidean, like an endless sheet. At least flat to within one part in a few hundred. That measurement alone tells us something profound. If the universe were small and closed, we would see curvature. We don't. Which means the universe must be either infinite, or at the very least, hundreds of times larger than the patch we can see. How much larger? Conservative estimates say that if the universe is finite, its circumference must be at least 250 times bigger than the observable sphere. Let that sink in. Our observable bubble spans about 93 billion light-years across. Multiply that by 250, and you get a cosmos at least 23 trillion light-years wide. That's the minimum, the floor. It could be far larger, possibly infinite, and there's more evidence. If the universe were small, like a closed loop, we'd see strange repetitions in the sky. Light would have wrapped around the cosmos, and the microwave background would show matching circles, patterns echoing across the heavens. Astronomers have searched and searched. No such patterns exist. The sky looks random, continuous, and boundless. All of this means that the horizon we see, the edge of the observable universe, is not the edge of everything. It's just the edge of what light has had time to reach us. Beyond that horizon, the universe continues. More galaxies. More stars. More clusters and voids, perhaps stretching forever. So already, our story has shifted. The observable universe is 93 billion light-years across, yes. But the real universe must be at least 23 trillion light-years across. And that number grows if we consider the next layer of the puzzle, the explosive birth of space itself, cosmic inflation. Inflation and the vast beyond. To understand why the universe must be older and larger than our familiar story, we have to go back, not just to the Big Bang, but to the instant before the Big Bang became hot. Cosmologists call it inflation. In the first trillionth of a trillionth of a trillionth of a second, space itself expanded exponentially. Not just fast, but unimaginably fast. A region smaller than an atom ballooned to cosmic scales in the blink of an eye. Why do we believe this outrageous idea? Because inflation explains mysteries that otherwise make no sense. Why is the universe so smooth on scales billions of light-years across, when distant regions could never have communicated? Because before inflation, they were in contact. Then inflation stretched them apart. Why is space so flat, with no detectable curvature? Because inflation ironed out any wrinkles, just like blowing up a balloon makes its surface appear flatter. Why don't we see exotic relics like magnetic monopoles everywhere? because inflation diluted them into invisibility. Inflation doesn't just solve puzzles. It makes predictions, precise ones. It predicted the spectrum of tiny ripples we see in the cosmic microwave background. It predicted the statistical fingerprints of the seeds that later grew into galaxies. And those predictions match observation almost perfectly. But inflation carries a consequence. If inflation happened, then the universe we observe, our 93 billion light-year bubble, was only a tiny patch of what inflation produced. Imagine zooming out from your neighborhood to see the whole Earth. Now zoom out from Earth to see the whole solar system. Now imagine our observable universe is just that neighborhood, and inflation blew the cosmos up to at least the size of the Earth, and probably far, far beyond. How far? Even the most conservative inflationary models suggest a cosmos at least 1023 times larger than the observable universe. In other words, if our observable bubble were 1 grain of sand, the real universe would be the size of the Earth. Other estimates push it even further, into scales so vast they blur into infinity. And here's the kicker: inflation might not have stopped everywhere. In some regions, it continues. Space keeps expanding exponentially, while in other regions it quenches, giving rise to bubble universes like ours. This is the idea of eternal inflation, a never-ending cosmic foam of universes, each with its own story. Which means the real cosmos is not just older and larger. It may be fundamentally without boundary. Our 13.8 billion year timeline? That's the age of our thermal history, the hot phase that began when inflation ended in our bubble. But inflation itself could have been running long before that moment. Perhaps forever. In that picture, the cosmos doesn't have a beginning at all, only local beginnings, bubble by bubble. So when we say the universe is 13.8 billion years old, what we really mean is our visible patch, our hot Big Bang, is 13.8 billion years old. The larger universe, the inflationary cosmos, is vastly older, vastly larger, and quite possibly eternal. The question of age. A cosmic clock ticking backwards through galaxies, stars, the CMB, then fading into darkness before the Big Bang. Here is where language betrays us. When we say the universe is 13.8 billion years old, what we really mean is something far narrower. The hot Big Bang phase that led to us is 13.8 billion years old. That number is solid. The cooling of white dwarfs, the ages of the oldest globular clusters, the half-lives of radioactive isotopes, the statistical patterns in the cosmic microwave background, all independent clocks point to the same. Answer: our thermal history began about 13.8 billion years ago. But what about before that? Did time itself begin 13.8 billion years ago? Or did something else precede the fireball? Several models suggest our Big Bang was not the ultimate beginning, but a transition. In bounce cosmologies, the universe once contracted, then rebounded. In that picture, the cosmos could be much older, perhaps eternal, with our hot phase just one cycle in an endless breathing of space and time. In cyclic or conformal models, aeons of universes unfold one after another. Each universe runs its course, thins into near emptiness, then gives birth to the next. In this view, 13.8 billion years is just the age of the current chapter, not the book. In eternal inflation, which we just explored, our Big Bang was simply the end of inflation in our bubble. Inflation may have been running long before, and will keep running elsewhere long after. Our 13.8 billion years is a local timestamp, not the age of the whole cosmic process. Even in the standard Big Bang framework, physics itself doesn't demand a beginning at 13.8 billion years ago. It only tells us that if we extrapolate our equations backward, we hit a wall where they break down. That wall is not necessarily a birth. It might just be a curtain we haven't lifted yet. So when you hear that the universe is 13.8 billion years old, remember, that's the age of our fireball, our horizon, our story. But the greater universe, the one beyond our bubble, may be trillions of years older, or infinite. It may have no beginning at all. In the end, 13.8 billion years is not the age of everything. It is the age of us. The unobservable universe. We live inside a bubble of visibility, the observable universe. Its radius is about 46.5 billion light-years. That's how far light has had time to travel to us since our Big Bang fireball. But here's the crucial point. That bubble is not the whole universe. It's just the part that light has reached us from. Beyond that horizon, the universe continues, with more galaxies, more stars, more voids, perhaps infinitely. Think of standing on the shore of an ocean. Your horizon is a circle around you, but the ocean doesn't end there. The observable universe is our horizon on the cosmic ocean. Now let's add another twist. The universe is not just expanding, it's accelerating. Dark energy drives galaxies apart faster and faster. That acceleration creates a cosmic event horizon. Right now, galaxies farther than about 16 billion light-years away are already lost to us. Any light they emit today will never reach us, not in a trillion years. That means the unobservable universe is not only what lies beyond 46.5 billion light-years. It also includes vast regions within that distance that are causally disconnected from us right now. We see their ancient light, but we will never know their present. And the sobering truth, over time, more and more galaxies will slip away. Billions of years from now, only the galaxies bound to our local group, Andromeda, the Milky Way, and a handful of dwarfs, will remain visible. Everything else will fade into darkness beyond the event horizon. So the unobservable universe is not a distant abstraction. It is reality itself, most of which we can never touch. Today it is already the majority of existence. Tomorrow it will be almost all of it. And that's the great irony of cosmology. The better we understand the universe, the clearer it becomes that most of it is, and always will be, forever beyond our sight. Speculative frontiers. If our universe is at least 23 trillion light-years across and possibly eternal, then what lies beyond our horizon may be even stranger than just more galaxies. One possibility is eternal inflation. In this picture, our Big Bang wasn't unique. Inflation continues in other regions, forever spawning new bubbles of space-time. Each bubble has its own Big Bang, its own galaxies, and perhaps its own laws of physics. Our observable universe is just one bubble among countless others, drifting in a vast inflating sea. String theory paints an even wilder picture, a landscape of possibilities. With hundreds of different ways to curl extra dimensions, each bubble could realize different values for fundamental constants, different strengths of gravity, different particle families, even different numbers of dimensions. Our universe might just be one oasis among a near-infinite desert of possibilities, one of the rare places where the laws align to allow life. Other models take time itself in strange directions. Roger Penrose's conformal cyclic cosmology imagines eons, whole universes expanding into near emptiness, then giving birth to the next in an endless cycle. In bounce cosmologies, contraction precedes expansion, so the Big Bang wasn't the beginning but are bound in an older oscillating cosmos. And some physicists even point to the quantum world, suggesting that every quantum possibility is realized in parallel, spawning an infinite branching of universes, side by side with our own. None of these ideas are proven. Some may never be testable. Yet they all converge on one humbling truth. The cosmos we see is not the cosmos entire. Our 13.8 billion-year thermal history is a local chapter. The real story stretches far wider and far older than we can observe. The frontier is speculation, yes. But speculation built on the scaffolding of real data, geometry, background radiation, expansion. The hints we see inside our bubble may be the fingerprints of something unimaginably larger outside it. Epilogue. The Bousso universe. Imagine a supersonic jet tearing through the sky, the air in front of it compressing into a glowing bow shock that races outward faster than the sound waves themselves. Now imagine that on a cosmic scale. What if our universe, the one we see and measure, is not the entirety of reality, but simply the expanding shock front of a greater event? What if the Big Bang was not the birth of all space and time, but the ignition of a localized fireball inside an older, larger, unobservable cosmos? From this perspective, the observable universe, our 93 billion light-year bubble, becomes the visible scar of that eruption. We exist inside the heated shell, the aftermath of the blast. The cosmic microwave background, that faint glow stretched across the sky, could be understood as the cooled residue of this shock front, the lingering radiation from a cosmic bow wave that marked the transition from chaos to order. The accelerating expansion that we attribute to dark energy might be nothing more than the ongoing pressure from the greater medium beyond, still driving the shock outward. Even the strange large-scale anomalies in the microwave background, the cold spots and peculiar alignments, could be seen as ripples and turbulence at the boundary of the shock, just as airflows downstream of a jet leave behind distorted eddies. This is not the mainstream picture. Standard cosmology insists that space itself is expanding, with no outside medium. Yet the idea of a bow shock is not so distant from other serious theories. Eternal inflation imagines bubble universes forever budding off into an inflating sea. Brain cosmology imagines higher dimensional membranes colliding, each collision sparking a fireball like ours. In both cases, our universe is not the whole but a local phenomenon. The bow shock hypothesis is simply another metaphor, another way of imagining how a local burst of energy could create a luminous bubble inside a larger, older backdrop. And if it is true, then the 13.8 billion years we assign as the age of the universe is only the age of the shock front itself. The medium it expands into could be unimaginably ancient, perhaps eternal, perhaps already scarred by countless other shock waves before ours, perhaps destined to host many more after. Just as a ripple on a pond eventually dissolves back into the water, our cosmic shock could one day fade into the background of that larger continuum, leaving no sign it ever existed. In this vision, we are not witnessing the totality of reality, but inhabiting the luminous edge of a disturbance in a far greater whole. The words observable and unobservable take on a haunting new depth. What we call the universe may be nothing more than a fleeting flare, a brilliant shockwave glowing briefly before vanishing into the eternal silence beyond. Some cosmologists have imagined the universe as cyclic, bouncing forever between big bangs and big crunches. But a new theorem by Rafael Bousso suggests these models are far harder to make work than previously thought. Entropy doesn't go away, and without some new physics, any contracting phase ends in a singularity, not a bounce. Still, alternatives like Penrose's conformal cyclic cosmology, eternal inflation, or entirely new physics may allow a cosmos far older than the 13.8 billion year story of our hot Big Bang. So here's the truth. The universe we can observe is 13.8 billion years old and 93 billion light-years across. That's the familiar story. The story of our thermal history, our cosmic bubble. But the real universe? It must be at least 23 trillion light-years across, 100 times larger than what we see, and likely much more. Its age? Far older than 13.8 billion years, perhaps without beginning. Perhaps eternal. What we call the universe is really just the part we can glimpse, a keyhole view into an ocean of existence. And as our telescopes sharpen and our theories expand, one truth only grows clearer. Most of reality lies beyond our reach. Galaxies, structures, maybe even whole other universes, forever unobservable but no less real. It's humbling, it's unsettling, and it's profoundly beautiful. We are children of a fireball, 13.8 billion years old. But we are also citizens of a cosmos so vast and so ancient that our minds can only touch its edges. When we gaze at the night sky, we are not just looking outward in space. We are looking inward at a mystery, one that reminds us that what we know is small and what we don't know is infinite. The universe is older and larger than you think.